And we're live again. Time for some fun and exciting calculus. Welcome to class. Um, all right, so let's get back to it. So last time we were talking improper integrals, and we want to kind of continue this discussion and sort of polish it off today. So first thing that I want to do is let's sort of consider let's consider the following integral. All right, so I've got this integral 1 over x to the power of p. P can be theoretically any number, positive, negative, integer, non-integer, whatever. And the question we want to ask is, under what circumstances does this thing either converge or diverge? Well, as you could probably expect, it's going to depend on the number p, right? That perhaps isn't a shock. In particular, last time we looked at two examples for two specific values of p where it converged and where it diverged. What were those two numbers that we looked at last time? Yeah, Jack? 1 and 2. And which one was which? For p equals 1, did we have converge or diverge? Uh-huh. And for 2, it converged. Okay. Uh, so what about if the number was less than 1, like a half or something? What about if the number is equal to 1? We've already answered that question. And what about if the number is bigger than 1? Okay, so it turns out that 1 is sort of the magic spot um, that that breaks this, but let's kind of see why. Um, so let's think of three cases. Okay, so p equals 1, we did last time. It diverged. Okay, how did we do that? Well, how do we think of an improper integral? What's the secret trick? Yeah, limit of a, not integer. Yeah, the limit of a proper integral was right. Okay, so we said limit as t goes to infinity of the integral from 1 to t, blah, 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 right? Or, and there's nothing special about the letter t. The only letter that I will not pick here is x because I'm already kind of using it for as a variable, and it's sort of bad form to use the same letter in two different ways. Right? That's just kind of sloppy. Um, okay, so that one diverged. Great. Now, for p bigger than 1, we did an example of a number that was bigger than 1, and that one converged. But that doesn't prove that it converges for any number bigger than 1, just that specific one. Okay, so what we need to do is do like we did with the p equals 2 example, but now with a variable, and we'll just leave it as p and see what happens. Okay, all right, so is that okay? That we've done an example, but that's not sufficient? Yes. Good question, and we'll see in a moment, actually. Yeah. You have to be psychic? No, not really. Man, I wish we had an owl cam in here. So it's that little camera thing. Yeah. So it turns out so the program I'm using here to stream is called OBS, Open Broadcaster Studio. Turns out that those things are compatible with OBS. So I just need to get it interfaced and figure out how to use it, and then
Yeah, you could like definitely see like if I was on my phone and you were like not in class, like you would definitely
yeah, because you'd been like,
yeah.
yeah. Okay, so yeah, how did we do this for the p greater than 1 example last time? Well, we just sat down and integrated it, right? So let me come over here and let's say the integral from 1 to infinity of 1 over x to the p dx will be the limit as, say, t or whatever, pick a letter. That, okay? All right, now here's where I have to think about the value of p. Okay, so this hopefully will partially answer your question, Cole, which is I'm going to rewrite this as x to the minus p. Same thing, right? And here's why I know that p equals 1 is sort of the special transition point. Because if I integrate x to the minus p, well, if p is negative, or sorry, if that exponent is negative 1, so p is 1, that's when I have to use a logarithm, right? Because what's the antiderivative of 1 over x? Log x, right? But if the exponent is anything other than that, I get to use the power rule instead, right? So what's the exponent here? It's negative something, but I assumed that p was bigger than 1, not equal to 1, yes? Okay, and as such, I get to use the power rule for the antiderivative step. And what's the power rule say? You add 1 to the exponent and then divide by that new value, right? So the exponent started as minus p. I added 1 to it, and I divided by that new value, okay? And this fact was predicated that the p was positive, namely it wasn't equal to 1, because otherwise I would have had to use a logarithm, and that's what we had to do last time. Okay, good. So far? Oh, that's what you were staring at me for, right? Okay, good, yes.
So is it x to the p power or just x times p?
Where? Here or here? X to the p power. Yeah. Oh, no, yeah, I'm sorry. That's just my sloppy handwriting. Yeah, no, I meant x to the p, right? Like that. Yeah.
So the bigger the p gets, the smaller it gets.
Uh,
Wait, that doesn't make sense.
well, it depends on what it means. So,
The bigger p gets, the smaller the values get.
yes. So, for example, x to the 1,000 in the, so 1 over x to the 1,000 is going to be smaller than 1 over x squared for most values of x, right? And think about that graphically, right? What's going to happen if you graphed 1 over x to the 1,000 versus 1 over x squared? 1 over x to the 1,000 is going to be like, this is why we definitely need an owl cam. Because those of you guys at home can't see what I just did. I'm doing like all sorts of fancy dance moves here, right? Um, maybe I need to throw a sound effect in there. Yeah. Okay. So yeah. So the bigger the exponent that's in the denominator, the smaller the fraction will be, and that actually sort of is a good point to which we'll return in a moment for something called a comparison test. Okay, so that logic is actually really useful. So we'll come back to that in a minute, Cole. Okay, so here's where I have to really use my thinking cap, because what did I assume that P was? Bigger than 1, correct? So if I negate it and then add 1, what kind of number is, if P is bigger than 1, that was our assumption to start with, what is negative P? Well, it's going to be less than negative 1, correct? Because that's how alligators work. You know, yeah, the inequalities. So those of you at home, I don't know how you do this in your elementary schools, but um, in American elementary schools, the inequalities, we're taught that they're alligators, and the mouth of the alligator always points to the bigger number because he's hungry, which means you've got to put teeth and spinities and maybe one of those beefy arms on the side for good measure. No, do you guys not know Trogdor the Burninator? Huh? Never mind. Trust me, 10 years ago it would have been hilarious. Um, all right, so right, so if P is bigger than 1, then negative P is less than negative 1, and if I add 1 to both sides, then that means that that exponent is less than 0, correct? Okay, that's important because that means that what happens as t goes to infinity of um, t to the negative p plus 1 over p plus 1, negative p plus 1, it means that that limit is 0. Okay, now let's think about why. If the exponent that's sitting on top of the t is a negative number, that means that we really can think about this as 1 over t to the something, right? Because what do negative exponents mean? Right.
But I thought P has to be negative, so it'd be positive then.
No. P is bigger than 1, so negative P is less than negative 1. So what I'm saying is that this quantity, right, sorry for everybody at home, this quantity right here is negative. I'm not saying P is negative, I'm saying the quantity negative P plus 1 is negative. Okay, good? Okay, so because that quantity is less than 0, then the limit of that quantity is 0. Okay, because this is like saying, what's the limit as t goes to infinity of t to the minus second? Well, that's really 1 over t to the second. And if t goes to infinity and you're dividing by giant things, then what do you get? 0. Okay? No. We may have to have more chats. Yeah. Okay. Okay. So, and if, yeah. Okay. So that limit is 0. Okay. Hence, oops, let me go back to, sorry, I meant infinity here. That means that the integral that we were considering, if p is bigger than 1, converges to that value. Okay, how did I get that value? Well, if I'm looking here, right, I need to plug in a t, I need to plug in a 1, and I need to subtract. Well, the part with the t plugged in goes to 0, so I can ignore him. And because I subtracted, that's why it's negative, that thing, and not positive 1 over. Okay, is that all right? So just fundamental theorem. No big thing. Okay. All right. So we've answered the question for p bigger than 1. What do you guys think is going to happen if p is less than 1? Probably the opposite, and you're right, it does. Okay, so can I move on to a new sheet, or are you still scribbling? We good? Okay, excellent. Okay, so your exercise is to show that uh, it diverges if p is less than 1. Okay, now, we've already showed it diverged for p equals to 1. Y'all's exercise, and do this weekend, just sit down and bang it out, to make sure that you're convinced that it diverges if p is less than 1. The argument or the logic is going to work very similar to what we did over here, except you're now assuming p is less than 1 rather than bigger than 1. Okay, so that'll tweak a few things. Okay. All right, so result. Okay, so the result that you're going to get is that it diverges. And so if we put everything together, then we get the following, which is called the p-test because of the exponent. Okay, so if you have an integral of that form, dx over x to the p, it converges if p is bigger than 1, and it diverges otherwise. Okay? That the statement of this makes sense. And we've proved 2/3 of that, right? We proved the equals to 1 case and the greater than 1 case, and then you guys, for personal gratification, are going to prove the other situation, just to make sure I'm not lying to you. I promise I'm not. But yeah. Okay, is that all right? Okay, so the next thing we want to do is kind of talk about, so Cole's observation about the exponents, okay, is somewhat important, okay? The other thing that I want to talk about is what happens if an integral is improper in multiple ways? Okay, that's a case we didn't deal with last time. Okay, then we have to be a little careful. All right, so I'm going to take as sort of a simple example here. This. Okay, now you might say, wait a minute, Dr. McKinney, we've just answered that question. That was the p-test. Except, what was the p-test? What did that apply to? It was the integral from, and this is most certainly not that. Okay, so first off, is this integral even improper? It's not to infinity, so it's not improper in that way. What's the, hmm? Yeah, if the function is undefined on the interval that we're dealing with, then we got a problem. Is this function undefined somewhere between -1 and 1? Oh, big time. Namely at 0. Okay, so at 0, we have a problem. And that happens to be where this function has a vertical asymptote. Okay, great. Okay, prepare to have y'all's minds blown. Let me switch over to Mathematica for a moment. And let me blow up the font so that everybody can see. Oh, that's why. There we go. I'm like, that is not 1 over x. Okay, so the integral is asking a question about area. Yes? Area between the curve and the x-axis. Okay, so what's the area, say, if the curve is positive between that and the x-axis? It's some sort of positive quantity. And how do we count area that's below the x-axis? We can count it as negative. Okay, it might not make geometric sense to talk about negative area, but we're sort of going to count anything below the x-axis as being a negative quantity. Okay, if you look at this picture, do you guys see any symmetry here? Yeah. Does the positive part of this graph look kind of like the negative part of the graph? Just flipped upside down, basically, and moved over and reflected, and then you guys did all that reflection nonsense in high school, right? Yeah. So, what might you be tempted to say here? Oh, they cancel out. Well, whatever's to the right is a positive something, and the stuff to the left is exactly the same geometrically, but it's going to count negative, so this should come out to be 0. Well, that would be what your intuition says. Okay, but what are we dealing with? Infinities. Thou shalt not use your intuition. Okay, and this is where your mind is about to be blown. Okay, so let's say equals, I'm going to put air quotes equals because it's not actually equal. Okay, it also means that I get to use a fun French word, naive, which has a double dots on the I to tell you that it's 2 separate syllables, not 1. Okay. All right, so the naive answer or the intuitive answer would be to say, all right. Oh, and I need to go back to the iPad for this, everybody at home. Um, okay, so for everybody at home, right, the intuitive answer, just thinking about this geometrically, would be to say it's 0. And it's not that. Okay, so here's sort of the issue. How do I have to think of an improper integral? Okay, that's okay. So how do we fix that? Can't do that just yet. We have to first think of it as a limit of a proper integral, right? How do we write the limit? Well, where's the problem with this integral? What value of x is the issue? 0, right? Because that's where we would divide by 0. So what I need to do is I need to think of this as being the integral from -1 to 0 I'm going to split it into 2 pieces, each one of which is improper still because they have 0 is a place where the function's undefined. Okay, so what I'm going to do is I'm going to think of this as I'm going to think of it like this. Okay, when I split it, each integral is improper, and the limit of a proper integral is how we'll deal with an improper integral. Okay, what did I write with the limits? Okay, there's 2 things I did with the limits. Okay, what are they? What's one thing I did with the limit? Yes. Okay. Okay, so I split up the integral, and then I wrote 2 limits. What's special about the 2 different limits that I wrote? Okay, they're two-sided limit, or sorry, one-sided limits. Okay, because if I'm approaching 0, well, I can approach 0 from two different directions, yes? Either from the left or from the right. And only one of them is relevant to each integral, okay? So for the first integral, I'm approaching 0 from the left because I'm over in negative territory. For the second integral, I'm approaching from the right because I'm in positive territory. Okay, does that make sense? Okay, so that's one thing that I did special with the integrals. Yes? Or limits, excuse me. What's the other thing that I did with the limits? I used A and B, not a single letter. Okay? And I have to use two different letters. Now, this is really hard to explain why you have to do this, but here's maybe a way to sort of think about it. If I have a quantity that's going off to infinity, how can a quantity go off to infinity? Are there ways to sort of go off to infinity faster or slower than other ways? Yeah, okay. So here's one way to go off to infinity. 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. Will that go to infinity? Yes. Okay. Now, here's another way to go to infinity. 1 plus 2 plus 4 plus 8 plus 16 plus 32. Will that go to infinity? Will it go to infinity faster than the first example? Yeah. It seems like it's going way faster, right? Okay. Now, if I had used the same letter here, what's to say that this first integral, that limit goes any faster or slower than the one in the second one? I don't know. But is it? No. Well, the integrand is the same, but that doesn't mean the thing I'm integrating is the same. Because notice that this one's -1 to a and that one's b to 1, right? Or okay, the a and the b, I've just been a little circular there, but my point is that I don't necessarily know that the first limit and the second limit are going at the same rate. Okay, and for those of you at home, I was using giant air quotes there. Okay, I don't know that, and this is why I need to use two separate letters, because otherwise I might get myself into trouble. Okay, and when we work this out further, you'll see why that would get you into trouble if you used A or B for both limits. Okay. I will say, guys, this is one of the hardest things to teach in Calc 2 because, like, to some extent, you just have to, yeah, it's kind of like imagine that you're in Sunday school right now, right? And I'm just telling you that, this is just how it is, right? And you just have to believe me, okay? I went to math seminary, namely graduate school, and I know what I'm talking about. Okay, so let's work out each of these limit problems. Well, first off, because I've written them as the limit of proper integrals, I get to do the um, fundamental theorem now, right? What's the antiderivative of 1 over x? Yeah, all right, so we got a natural log here from -1 to a, and then we still have the limit as a goes to 0 from the right of that dude. Left, left, right, no, left. Oh, the bar. That just means, right, so what does the fundamental theorem say to do, right? You take the antiderivative, you plug in the top number, you plug in the bottom number and subtract. The little bar to the right with the two numbers tells you plug in the top number, plug in the bottom number and subtract, but you're finished with the integration part. Okay, that's all it means. Yeah, okay. All right, and then we had b going to 0 from the right. Oops, I'm sorry. That should be natural log of Okay, so plug in your A's and B's and 1's and stuff. So here I'll get natural log of A minus natural log of, and here is why I'm such a stickler about the absolute value. Okay, because right here, otherwise I would have a problem. All right, and then this last one is like so. Okay, question, preguntas, fragen there. Now I can simplify that, and we still got more work to do, but are we cool with that step? Well, 1 and -1, because those were that was the bounds of the original problem. Yeah. Okay. What is the log of 1 and the log of, so this term and this term both do what? They go to y. What's the log of 1? Mm-hmm. And so the log of 1 is 0, right? That's what the logarithm does. Now, this is why the absolute value is so important, because otherwise I'd have a log of a negative, and that's verboten. Okay. So, but I don't really have the log of a negative because I take the absolute value, I get 1. What's the log of 1? 0. Okay, good. Okay, so now I'm at the point where I need to take the limits. So let me, sorry, these two terms go to 0, so I can ignore them. And what I'm left with and this should be a minus right there. Okay, good. So what is the value of each limit individually? This trap, what's the value of the first limit? Okay, which is what? Uh-huh. Okay, and what about the right one? Sure. Which is? Okay, but it's negative, so it's okay. Now, let me go back to Mathematica to convince you that we're not full of it here. Okay, so this is the graph of, here, let me go out to 2. So, oops. Okay, the graph of natural log looks like that, right? What happens at 0 for the graph of natural log? We got a big old fat vertical asymptote. Okay, okay. All right, vertical asymptote, great. As x approaches 0 of, all right, now I don't have the absolute values in here, so let me actually throw that in to my plot, like so. Okay, and let me just symmetrize this for sake of a good picture. All right, if I throw the absolute value in there, then that's the graph of it, right? It's sort of symmetric about the y-axis because of the absolute value. So what happens as x approaches 0 here, either from the left or from the right, it doesn't matter. What is this function doing? It's going to negative infinity. Okay, so the limit that we're dealing with, this one is minus infinity, and that one is minus infinity. All right, what's minus minus infinity? Right. It explodes. No, not really. Yeah, it'll say error undefined, something like that. Yeah. Huh? Yeah, that too. Right. If you get a cheapy one, it might literally explode. No, not really. Right. Okay, so we get infinity minus infinity. What is infinity minus infinity? Now, what are you tempted to say right here? You're tempted to say zero because you say, oh, well, anything minus itself is zero, right? But that's only true for numbers. Who said that infinity works that way? Is infinity a number? Not really, which is to say no, because you either are or are not a number. Okay, this is not, this is the axiom of Hamlet, right? To be or not to be. You don't get anything in between those two. Oh, you don't, come on, surely you know Hamlet. Yeah, it's better in the original Klingon. Um, actually, Hamlet's really difficult to render in Klingon because, well, what's the famous part of Hamlet? The most famous words: to be or not to be. To be, that's an infinitive, right? Okay, and it also involves the word being, right? To be. Well, guess what Klingon doesn't have? A verb to be or an infinitive. Oh, it's a made up language from Star Trek. Yeah. I'm not fluent, but yeah. So in Klingon it's tah pa tah be, which means literally he continues or he does not continue. That's the best you can get in Klingon to that. So okay. All right, so what's the naive answer here is to say infinity minus infinity is zero. We cannot do that. Okay. Um, like, for the same reason, what's infinity divided by infinity? Same problem, right? This is when we were talking about indeterminate forms. I guess this was last week, right? When we talked about L'Hopital's rule, we said infinity over infinity, it would be tempting to just say it's equal to one. Okay, but it doesn't work that way, right? And we have to use techniques like factoring or L'Hopital's rule or other algebraic voodoo to figure things out. Okay. Well, this is sort of the same problem. This is an indeterminate form, and it's not really, it's unresolvable. Okay, so we're hosed. Okay, so the moral of the story is that this integral diverges. And the way to think about that is, what does it really mean to diverge? What was our technical definition? What did it mean to converge? It converged if the limit went to a specific number of some sort, right? And it diverged if that wasn't true. So does this go to a specific number? Yeah. If it doesn't converge, it diverges. There's no in between, conditionally. Okay. Um, wink, wink. Okay. So, yes. So you have to be careful with the limits here, is what I'm trying to say. Now, sometimes, depending on the thing you're integrating, sometimes things work out fine, no issues. This is not one of those examples. Okay. Um, okay. All right. So let me go on to sort of the last sort of idea here, which is called a comparison test. Okay. So let me take an example. Let me make sure I'm back on the thing there. Okay. Oh, crap. It does help if I plug this into the battery.
So when we wrote one of the pages before, we wrote like P is less than or equal to
Mm-hmm.
one. Is that means it diverges? So
If P is
that rule is like greater than or less than or equal to.
uh,
That diverges
yeah.
or the case.
Uh, yeah, no, I know what you mean, but okay. Well, it's a good thing that my laptop's going to die in a minute because Okay, the stream may die. Oh no, I think actually we're okay. Yeah, maybe, we'll see. Well, now it says service recommended on the battery status, and it doesn't want to charge. It's a good thing I got a new one, because this is now the fourth problem and the reason that I need to just throw this thing out the window. So, okay. Right, so I'll try and be quick about this in case the stream just dies on us. Hopefully that won't happen. All right, 1 over x squared, that integral, does it converge or diverge by the p-test? Converges by the p-test. Okay, so let me change the question slightly. With the bounds and the exponent, the two. Okay. Okay, so converged. Great. Now, let me change the question slightly. And let me think of 1 over x squared plus 1. Okay. Now, what would be your gut here, converge or diverge? Why? Yeah, it looks like I really haven't changed much from what I had before. This looks a lot like what I had a minute ago. Okay. And you're right. All right, so let me think about it this way. Let me go back over to Mathematica, and let me graph two functions. I'm going to plot two things, 1 over x squared and 1 over x squared plus 1. And I'm going to plot them from 1 to, say, 10. Okay, I can't go off to true infinity because, oops. Okay, this thing is literally about to die. Let me fix that because I don't want the stream to cut out on me. Let's see how fast Dr. McKinney can. Come on, come on, come on, come on. Ah, saved. Okay. Huh? Yeah, well, that's because it's so close to death that the estimates are bad. I don't know why it doesn't want to charge off my new one here. Of course, the heat may not be helping it, but whatever. Okay, so good. So let's look at the graphs of this thing. So in blue is the graph of 1 over x squared, and in orange is the graph of, and in fact, let me actually make one minor tweak here. There, okay. So wonderful. So the blue one's 1 over x squared. The orange one's 1 over x squared plus 1. What can you tell me about the orange curve? The orange one's 1 over x squared plus 1. So you see the order that they're written in? Blue first, orange second, and that's Mathematica's default order. Which one's smaller as a function? The orange one, right? Smaller y values.
Yeah.
Okay. All right, now things get a little bit misleading when you get up to like x equals 6 because it looks like they're right on top of each other, right? And they're not actually right on top of each other. It's just that it's so close that you can't tell the difference visually, okay? But over, say, at x equals 2, it's pretty obvious that one of them's a little bit less than the other, yes? Okay, so the integral is asking the question, in the first integral, 1 over x squared integral, what's the area between the x-axis and the blue curve? Is that going to come out to a finite value or not? Well, it's going to be a finite number because that integral converges. And for the moment, I don't care what number it actually is. I just care that it is one. Okay, So the orange area would be the area between the x-axis and the orange curve. Is that less than or bigger than or equal to the area under the blue curve? It's definitely less than. Well, I just said that the area under the blue curve is finite. The area under the orange curve is less than that. And so what must the area under the orange curve be? Also finite. Okay, so this is called a comparison that we've just made. We've made the observation that this, well, here, let me say it this way. We noticed that, oh, let me switch back over to the iPad for everybody. Sorry. We noticed, graphically, and we could sort of think about why this is true algebraically, that 1 over x squared plus 1 is a smaller quantity than 1 over x squared. Okay, graphically we saw that. Algebraically, why does that make sense? Well, if I add 1 to the denominator, that means the denominator is bigger. What happens if you divide by a bigger thing? You get a smaller thing, okay? But, of course, because 7 out of 5 Americans struggle with fractions, so here's a good story. So what's McDonald's probably most famous hamburger? Well, okay, besides the Big Mac. Right, the quarter pounder with cheese. So back in the 80s, I think it was, uh, another burger chain decided that we're going to advertise the third pounders. Okay. And then, we're going to have a third pound hamburger, which is bigger than a quarter pound hamburger. Yes. But it flopped because stupid Americans thought that a quarter pounder was bigger than a third pounder because 4 is bigger than 3. Womp womp. Okay, so yes, cool. Oh, well, different unit system, but yeah, yeah, okay. So the joke was newtons versus pounds, but yeah. Okay, so the 1 over x squared integral is less than, or sorry, the function is less than the other function, and so hence the integral so the latter integral converged by the p-test. Okay, we've already proven that. And therefore, what can we conclude? We can conclude that the x squared plus 1 function, that integral also converges. Okay, it's a thing that's always smaller than something else that converges, therefore it also converges. Now, here's the annoying thing. Do they necessarily converge to the same number? No. They just both converge to numbers, plural, finite things. Those values may be different, and in fact, they are, because um, um, this integral is, and then we'll quit. So I'm going to write real fast here. Sorry. This one actually converts to pi over 4 because x squared plus 1, in the denominator, his antiderivative is arctangent. And because I know my trigonometry, I know that the limit as t goes to infinity of arctan t is actually pi over 2. There's a horizontal asymptote in the graph. Okay. All right. I sped through that, and I'm sorry. So you'll be okay. All right. We should probably quit here. Um, and I will see you guys on Monday.